Hello everyone, Dylan here, and although it is December 11th, welcome to Advent of Code Day 9, 2025 in Python. And sorry this video is late, but to be honest, I probably put about 6 or 7 hours into solving it. I think my theory was pretty good, but due to the nature of the data, the size of the numbers, it ended up requiring a technique I wasn't very familiar with. And not only that, I had work, I needed to sleep, so here we are. Anyways, I'm going to do my best to explain what I believe is quite a complicated solution. So strap in and let's get into it. So what we have here is a big movie theater with some tiles on the ground. And the elves give us a list of red tiles, which we can see arranged here in this grid. And these tiles are going to be used to make squares, basically to change the decoration. So part one of the problem here is actually, it's really simple. Using all possible combinations of red squares, what is the biggest square of tiles that we can make? So let's go ahead and look at the code. So starting off with just parsing my data here, I'll go ahead and say that data is equal to line.split, splitting on the comma, for line in data, and then we'll just go ahead and return a bunch of points turned into integers. So take int of a, int of b for a b in data. Okay, and if we take a look and say that our points, let's just say our corners, are equal to parse data. Okay, and using the example points from the Advent of Code website, just for simplicity, you can see that if we run that, we go ahead and get the correct points here. Okay, so let's find the largest area. We'll just say largest is equal to 0, and let's check every combination of points. So for point A in range, and we'll go from the length of our corners, and we want to go to everything except the last one, and then for B in, and we'll start from the second item in the list and go to the length, the whole length of the corners. So that way we get every combination once, and we'll just say that x1, y1 are equal to corners of A, and x2, y2 are equal to corners of B. Then we'll just say that the area is equal to the absolute value of x1 minus x2. And we want to add 1 in case that either x1 and x2 are the same or y2 and y1 are the same, because we can have one that is a 1 by however long. And then we'll multiply that by the same thing in the y direction. Also remembering to add a 1. And then we can just say that if area is greater than largest, then largest is equal to area. And then we can just go ahead and return largest, and let's see what we get. Okay, making sure that we say for B in range, 1 to length corners, let's give it a run. Okay, for the test data we get 50, and for my actual data, getting this long number here. Okay, let's go ahead and test it out. All right, nice and easy, we got our first gold star. But this is where the problem really picks up. So what do we got here? Well, it turns out there are also green tiles, and we can only move the red or the green tiles. So red tiles are here, the hash marks. These are our corners. And then it turns out that if we kind of go in a path the way that the points say, so say for example, this is our starting point here, we go to the next point, then the next point, then the next point, then the next point, and so on, wrapping all the way back to the beginning, then all of those borders that we just drew between points become green squares. And then consequently, anything left in the remaining enclosed area is also a green square. So our new problem is what's the largest square we can make or rectangle we can make using only the red or the green cells that are enclosed here. Now, for such a problem like this, it seems not so difficult. Maybe you can just fill in the box, or maybe you can, my original idea was to check just the four corners of each potential shape that we can make and see if they're in this box. However, if we go ahead and take a look at our puzzle input, you can see that our largest numbers here are absolutely gigantic. I mean, we're all the way up to 100,000. And it turns out that with such a problem, even just finding the entire fill of the shape takes a long time. In fact, too long. So what can we do about it? And the thing that we also need to consider is all the possible shapes. So, because we can have shapes like this, where basically it could look like where all the corners are in the shape, but there's obviously a gap in the middle here. And future Dylan here, before we get into the code, I just want to mention that although I have the theory on how to solve this problem, and my solution originally did work on the input from the website, the sample input, my solution was actually too slow for the full large input. And I would like to give credit where credit is due. I watched a video for my reference and I learned a new technique called coordinate compression, which I'll explain in this video. But my original solution was complicated, and without the help from this other channel, I don't think I would have solved it today. So you can find the link to that video down in the description below. Now let's get into the solution. Okay, so starting off here, I'm just going to outline the function headers that we're going to need. So first, let's go ahead, and this time we're going to declare corners as a global variable. That way it can be accessed easily from all the functions. So say global corners is equal to, corners originally is equal to parse data. And then with our borders, we should be able to, or corners, we should be able to get a border from the list of corners. And then given a list containing all the border points, we should be able to fill in that shape. And that should take border, and that will be a set of points. That should go ahead and return a set of points as well. And to stay organized, I'm just going to keep all these functions under our shape. Okay, and then as I've alluded to, we are going to handle the coordinate compression, and I'll explain more in just a moment once we get here. But basically what coordinate compression does is it takes a really big shape and it just looks at the interesting points and to give us a much smaller grid. So under coordinate compression, we're just going to need to compress our region given some points. And because we'll be dealing again with global variables, we're actually not going to need to return anything. And then given our compressed point mapping, we should be able to go ahead and find or look up some point I. And this will return a tuple of int being our points. And the last thing that we will want to do up here in the shape is write a check function eventually to check if some square is valid. So we'll take in a shape, which would be a set, a filled in set of points, and we'll check for 2 points x1, y1, and x2, y2, and this should return a bool. So what we're basically going to do here is we're going to get, we found our corners originally, and then we're going to compress down the shape into a much smaller grid. And then once we have the compressed shape, we will get the border of the compressed shape. then we'll fill that shape in. And then for any combination of red corner points, or I guess their translation in the compression space, then we'll check if that square is valid. And this would, with a simple enough data set, this would actually work without the chord compression as well. But because our points are so big, we got to compress the chords. So let's go ahead and see, how do we compress the chords? Well, let's go ahead and take a look back at this example input. Now, we have this whole big shape, but really only interesting things happen at these corner points, these inflection points. Because even if we have, some shape like this, or if we're trying to make the square like this, then we just need to check the points around the corner, kind of around the border, because if the border is no good, then the inside points also are no good. So basically, by just looking at the interesting points, which are these corners, then we can kind of shrink the grid down by labeling a bunch of points in this y direction and a bunch of points in this x direction. So like here we have 1, 2, 3, 4, 5, 6, 7, 8, 9 rows, and I don't even know how many columns, but we can press it down, the rows, to say row 0, row 1, row 2, row 3. And then columns from here, column 0, column 1, column 2, column 3, where each column is representing a column where something interesting happens. And so the way that works out is basically, however long this list is, I do believe it's around 500 points. That means our grid is, instead of being 100,000 by 100,000, our maximum size of the grid just becomes the number of points that we have in this list. So in this case, it's going to be 500 by 500 grid. And 500, 500, although big, is definitely small enough that our computer can handle checking through it. So let's go ahead and see how the compression algorithm works. So the first thing that we're going to do here is, before we even jump into compression, let's go ahead and write how we are going to get the border. And so the first thing we need to do for our border is handle the fact that when we get to the end of the list, it wraps back around. So the first thing we should do is corners append, and we'll just append the first item. We'll copy it to the back of the list. That way we go ahead and make sure to close the loop. And then we'll just go ahead and say that the border that we're trying to make will be a set. And so I'll just say for, let's just say I in range length of corners, and we'll go -1 here because we're always going to look at this point I and the head and the point ahead of it. So x1 and x2 are equal to corners of I, and sorry, that should be y1, not x2. Now x2 and y2 are equal to corners of I plus 1. And then let's check the case where we're going to a point that is vertical. The next point is vertical. So x1 is equal to x2. We're only changing in the y direction, so y1 and y2 are going to equal, and we want to make sure that y1 is always less than y2. So I'll say sorted y1, y2. That way y1 is always less than y2, and for y in range, y1 to y2 plus 1, basically making sure that we go all the way. Then borders dot add x1 or x2, doesn't matter, and then the y that we found. And then in the horizontal direction, basically the opposite. If y1 is equal to y2, then x1 and x2 are equal to sorted x1, x2. And for y in range, just kidding, for x in range x1, x2 plus 1, basically, and the plus 1 is to make sure that we include the corner point as well. Borders.add, and this time x and y1. And then at the end, we can just go ahead and return our border, making sure to spell border correctly here. So now I'm going to say our border is equal to get border of our corners. So going ahead and fixing this check function header, y1 to y2, I will go ahead and take a look at what this looks like. So we can go ahead and see all of our border points are here, but this isn't very helpful. So I've actually gone ahead and written these two functions here to find the size of the grid and then to generate a grid in visual representation. And these aren't essential to the solve, so I'm not going to explain them, but if you want to, you can pause and see how they work. But what we care about is we can say that our grid is equal to get or gen grid of our border. And if we go ahead and run this again, we can actually see our points in the border here. And this is awesome. So this is going to give us a little clue to how our code is working. So now that we have gotten the border, it is time to compress our points. And we are going to go ahead and store the compressed points, or the compressed corners, if you will, in a function that I'll call just comp corners, not a function, a variable. So in order to do this, and I'll go ahead and add comp corners here as equal to a list. And then we're also going to need to have two sets of dictionaries. One set will store our compressed coordinates, and then the other set will store the information that we need to look up the original coordinates from the compressed coordinates. So for the compressed coordinates, I will say that the compressed x and compressed y are equal to empty dictionary and empty dictionary. And then also we need to be able to reverse look up the x and y. So we'll say reverse of x and reverse of y are also equal to dictionaries. So the first thing that we need to do is find all the x's and the y's separately. So we'll say x and y are equal to sets, and we'll just say for x and y in points that we've taken in, then we'll say x dot add x and y dot add y. And then let's create the mapping. So as I explained, we're basically going to take this row and make it 1, and then 2, and then 3, and then 4, and then the y direction 1, 2, 3, 4. So what we'll do is use enumeration. So we'll say for the index of x and the x itself, in enumerate, and we want the x's in order for sorted x, capital X there. Then we'll go ahead and say that our compressed x, and we'll find that with the actual original x value, and that's going to equal to I. And then we'll say that the reverse of x, so given some I, which the I is the coordinate in compressed space, then we can find the original value x. And we'll do the same thing for the y's, and we don't need to return anything because, yeah, we're just updating global variables here. So let's see if we can go ahead and visualize what's going on here. So if we go ahead and take a look, we'll leave this grid, which will be our original grid. And then we'll just go ahead and say compress. And we want to compress the corners. So that'll be our global corners all the way up at the top. And if we compress our global corners, then we'll expect to find all the points in the mapping. So we can see that, I'll just go ahead and generate a grid. We'll get our compressed grid is equal to gen grid on the compressed corners. So let's go ahead and run this. And actually, we haven't generated the new points, so we can't look at the compressed grid yet. But if we do take a look at our global variables here, then we can see that all the points in our original data, the original data was 0 by 11, then our keys here in the reverse lookup are actually our points, our coordinates in compressed space. So the keys just 1, 2, 0, 1, 2, 3 show that our compressed space will actually just be 4 by 4 for this problem. Now let's go ahead and write this find function, because the find function will actually be able to take in an I, which I is an index from our original corners here. So 0, 1, 2, 3. And given this corner, it will go ahead and use the comp x and comp y to find the coordinate in compressed space. So for example, if we take index 1 here, then it will go into x, and we'll see that index 1 had the x value 11. So go to comp x, find x11, and that compressed coordinate, that compressed x value will be 3. So we'll just go ahead and say that our x is equal to the compressed x's, and as our index here, we want to find from our original points or corners and of I. So go into, like I said, if we're taking a look at this one here, if our I is 1, then we'll go ahead and take the x and the y value from that. So corners I and that, and x would, or 0 would be the first number in the tuple. And then y is going to be equal to the compressed of y of corners I, and the y value is the second one. So that one there, and then we'll just go ahead and return xy. So we'll just say that compressed corners is equal to, and we can just say lookup or find I for I in range length of corners. So basically for each corner in I, go find its compressed value and put it in compressed corners. So now if we look at the compressed grid, I'll go ahead and debug, and our original grid is quite large like this, but now our compressed grid is just 4 by 4 as we expect, and well, it's still not the borders yet. So let's go ahead and say that our compressed border is equal to get border of our compressed corners. And so then if we pass compressed border into our grid function, we can see that we get a nice 4 by 4 grid here. So the next step that we should do is fill in this compressed shape so that we can check all the possible squares against it. But in order to do that, we first need to find a point inside this grid. And that's actually a little bit of an interesting problem because, well, we could kind of search forever, but that's really, because we could kind of search but then we'd have to check in all directions if it finds a border, and then we can know if it's a point. But we can actually calculate it by looking for a corner such as this, and then looking one in here. So I am going to find on the farthest right side, or the farthest left side, what's the lowest y value. And that'll guarantee that we find a corner like this. But you can see in this case, there actually is no inside point. There's only border and border. So here's another idea, the last idea that I got from the solution, which I'm linking below. And that is we can actually, since we have this compressed space, we can actually just double the size of the compressed space and guarantee that we'll get a point inside. So the way that we can do that is just for I, we can multiply I by 2 for all instances of I in our compression. And if we go ahead and run our debug again, we'll this time see that we've doubled the size of the grid, but we have we're guaranteed to everywhere have at least one square of inside, which means we'll be able to calculate the location of a square inside the grid, and from there use a depth first search or breadth first search to fill out the entire grid. So let's go ahead and do that, and I'm actually going to do that just in the fill shape function from up here. So in fill shape, we're going to want to return from the border points. We're going to want to return the filled set of shapes, or shape of sets, or points. So first we need to find a point inside the shape. And first, to do that, we will find the minimum x. So we'll go ahead and say that our min x is equal to some big number. Let's just say, I don't know, 100,000. And we can also go ahead and say our min y is equal to the same thing here. And we'll go ahead and say for x, and we don't care about the y for now, in the border that we gave in, which in this case will be our compressed border, then we'll just say that min x is equal to x if x is less than min x, else keep it the same, else min x. And then we'll just say for y, and we're going to make a new list here of just y for x, y in border, only if x is equal to min x. So we really only need to check the y points on the same line that the minimum x is on. Then the same thing, min y is equal to y if y is less than min y, else min y. So we have our min x, we have our min y, and that means we have found this point in the grid here. And let's just go ahead and verify that. I'll go ahead and return min x, min y, and down here if we just say min x and min y are equal to fill of our compressed border, and we should call that fill shape, then we can see that for x and y we get the value of 0 and 2, which checks out. 0 in the x and 0, 1, 2 in the y. So let's go ahead and just say, and then let's just say that our x and y in the grid are going to be equal to min x plus 1, min y plus 1, and then if we go ahead and return x and y and run this again, we'll see that this time it's 1, 3, and if we look in our compressed grid, x equals 1, y equals 3, it's a point inside, the point right next to this corner. So now let's actually fill the grid. Okay, so I'll add in that these are the directions that we can traverse in, and we're gonna use a queue of points to check. And so we'll just say that check is equal to, and initially it's going to be the points in the 4 directions from the corner point that we found. So we'll say x plus dx and y plus dy for dx, dy in ders. And then while the length of check is greater than 0, so while there's something to be checked, let's check it. So let's check the first item in that list. So xy is equal to check.pop, which will also remove it from the front of the list. And if x and y is in the shape, then we can go ahead and continue. So if I go up here to shape, and if I initially set shape to border, and we want to go ahead and copy it so we don't actually accidentally affect border. If we say that the shape is equal to border.copy, then if x and y is already in the shape, and on this first round that would be the corner points or the border points, and in further rounds it would be anything that we've also found inside, then we don't want to add it again, so let's just continue. And then now at the very end, we can just return the shape. So if we go ahead and check our work down here, this time let's go ahead and say that shape is equal to fill shape, and this time we'll say that our grid is equal to gen grid of the shape. And let's go ahead and make sure that I didn't make any syntax errors. We'll go ahead and debug. And actually, let me do that one more time. Let me add in a new breakpoint. So originally, here's our grid. And then after filling the shape and computing the grid again, you can see that our shape is all filled in. So now that we have a filled in shape, then we need to go ahead and check all the possible combinations. So let's go ahead and now find the largest area. So again, largest is equal to 0. And this will be basically the same as last time. So for A in range, len, and we want to use our compressed corners, -1. And for B in range, length of our compressed borders, or corners rather. And this time, again, just like last time, we want to start at 1. So this will check all the combinations of corners in compressed space, greatly reducing the amount of work that we need to do. And we'll go ahead and say that x1, y1, x2, y2 are compressed corners. And we have two options. We could either check the square first and then compute the area, or we can compute the area and only check if it's actually valid for anything that the area is larger. And it turns out that actually it's significantly faster to check the area first. So that's what we'll do. We'll go ahead and we need to look up the original points in order to calculate the actual size of the area. We don't want the compressed area. So let's just go ahead and say that XA and YA are equal to reverse X of X1 and reverse Y of Y1. And so that should look up the original coordinates. And then we'll say XB and YB are equal to reverse of XB, or sorry, X2, and reverse of Y of Y2. Okay, so let's get the area, and the area will be the same formula as before, making sure to use XA, XB, YA, YB for the reversed. And so if the area is greater than largest, then we can go ahead and say if check, and remember we're going to pass in our shape, and we still want to use the uncompressed coordinates because we have the uncompressed, or the compressed coordinates because we have the compressed shape. We'll give it x1, y1, x2, y2. So if check is okay, then we'll just go ahead and say largest is equal to area. So let's go ahead and write check. So for check, we are just going to do check every single point in the square, which it may take a bit of time, but it's okay because we are in compressed space. So the first thing that we'll do is order x1, x2, and y1, y2. And let's just go ahead and check every point. So we'll go ahead and say for x in range, and this time x1 to x2 plus 1. For y in range y1 to y2 plus 1. If not, xy in shape, then return false. Otherwise, if we get to the very end, then we can return true. And of course, this should be if not xy in shape. Okay, so let's just go ahead and give this a run. And according to the website, the solution for this problem should be 24. So if we go ahead and return largest, what do we get? Okay, and we get 24. So let me go ahead and test this on my real data. Okay, and starting to run here. Okay, and here I've got my answer, and I just want to mention that I definitely commented out these generating grid things because that was significantly slowing things down. So let's go ahead and test this input. All right, moment of truth, and 1 gold star. So going ahead and recapping what we did here, after finding our corners, we went ahead and compressed those coordinates down into a smaller space that only had points where something interesting happened. And this whole compressed coordinates was the key to this solution. And I don't even think this border was necessary here. And so one more time. And so then once we had our compressed shape, then we could run the algorithm where we could check every position for every square to see if it were in the compressed shape, and then just using the reverse lookup to find our actual points and calculate the area. So that does it for day 9, Advent of Code. And although it's late, I'll be trying to catch up on day 10 tomorrow. So if you have any questions, please leave them down in the comments, and I'll see you next time. Bye.